Hi, everyone. My name is Eva Say. I manage the Big Data Services team at Netflix. Today, I'm very happy to be here, and along with Kurt Brown, we're going to talk about how we use Amazon S3 as our centralized data hub. And through that lens, we're going to talk about the big data processing engines that we use, the big data ecosystem that we built, the architecture we choose, and the tools and services that we built. So let's start by saying that S3 is in the center of our big data universe, and we will use that to weave a story about our architecture. When we first started, using S3 is a great intuition that we have. It is intuitive because it is a cloud-native service. It is free engineering, although it's not free, of course. It is practically infinitely scalable in terms of storage. It is 11.9 durable and 4 nines available. It also allows us to decouple compute and storage, and which is a great architectural choice and intuition we have, and I'll cover more about that later. It is also very counterintuitive. There are actually engineers at Netflix questioning why we choose to do that. It is counterintuitive because S3 is eventually consistent, and also there is performance impact. S3 nonetheless is a cloud-based service that is remote from your cluster. So there is performance impact, and I'm going to talk a little bit more about how we do the trade-offs in the later slides. So our current data hub scales is we currently have 60 petabyte data with 1.5 billion objects and more. In terms of data velocity, on a daily basis, we ingest about 100 terabyte of data. We read about 3.5 terabyte daily in our ETL processing. Then we write back 500 terabytes. And we also expire about 400 terabyte a day. So as you can see, there's a lot of data that's churning through our data hub on a daily basis. There are two main data ingestion pipelines in our data platform. The first one is the event data pipeline. These are business events. These are generated when you search for a title or when you click play on a title. We collect around 500 billion of them per day, and it has a 5-minute SLA to arrive in our data hub. This is a rough architecture of our event data pipeline. Netflix is hosted on 3 different regions. In each region, there is a Kafka data pipeline. Cloud application is going to send the event to the Kafka data pipeline. And then the Kafka data pipeline cluster is going to write these events in files into the regional S3 buckets. After it has done that, it's also going to issue a message on the SQS queue to put the key name on there. Downstream is the Ursula system, which is the event ingestion pipeline that the big data platform built. So what it does is basically consume the SQS events across all 3 regions and read the file directly from S3. In this architecture, it allows Ursula to read the file much sooner in a more near real-time fashion because Ursula is reading around 6 million files a day across all the different regions. It also allows Ursula not needing to list S3 continuously to discover new files and also not need to handle eventual consistency issue. So basically, at this point, what Ursula does is to group and merge these events based on Kafka topic and then publish it onto the data hub. So when an event started from the cloud application to the point that it arrived at the data hub, it's around 5 minutes. So there is a second data pipeline. That's a dimension data pipeline. Some of you might know at Netflix, we use Cassandra as our online data store. We store stateful data in Cassandra. These are data like subscriber data. We have over 100 Cassandra clusters, one for each data set. And we extract from about 40 of them as dimension data and put it in the data hub. We do daily extracts. And for the more time-sensitive cluster or information, we do every 4 hours or 6 hours data extract. Again, this is a high-level architecture of what it looks like. As I mentioned, there is one Cassandra cluster for each data set. It's replicated across 3 different regions. The Cassandra cluster is going to write incremental backup file as well as snapshot in SS table format onto the regional S3 bucket. Downstream is the AWS system that we built. It is a bulk data extraction pipeline. It is also open source on Netflix OSS. And what it does is basically process these SS tables from a preferred region, and do transform, generate a dimension table, and put it into a data hub. In case the backup SS table is not available in the preferred region, AWS can also consume from an alternate region and do the data extract. So in this architecture, you can see that AWS is actually listing these files on S3. And the reason why we do it is because AWS is doing daily extract, and also there's not as many files as the event pipeline. However, we are working on the second version of AWS right now to do the event publish notification framework just like Ursula. And the reason is we want to decouple the upstream SS table generation from the downstream consumption model. So let's take a look at our transform and data processing architecture. So we have two rationale when we do the architectural choice. The first one is that data is gold. We can afford to lose a clusters or clusters, but we cannot afford to lose any data. The second rationale is that there is no one-size-fits-all in the big data processing world. Some engine is good for low latency, some are good for high data throughput. So we want to have an architecture that allow all these different engines to interoperate on the same set of data and let our users choose the right engine based on the SLA and the constraints that they have in mind. So here's a rough high-level architecture of our data processing engines. So Hive and Pig are for ad hoc and ETL processing. 2 years ago, we introduced Presto in our architecture. It is for interactive ad hoc querying. So Presto today already largely overtake the Hive use case. At the beginning of this year, we introduced Spark. We're hoping that Spark will be eventually the ETL engine of choice and overtake some of the Pig use cases and all of the Pig use cases eventually. And Spark also supports machine learning algorithm, so it would allow our platform to actually include additional use cases. Currently, Hive, Pig, Spark are all running on top of Hadoop Yarn clusters. We're running Amazon EMR clusters. Presto is directly running on top of EZ2. We have a couple of really large Hadoop Yarn clusters. Together, they are around 3,500 D24XL. For Presto, we also have a couple of clusters, and together we have around 250 to 400 R34XL. It is a range because we do expand and shrink the cluster, the Presto cluster, based on availability of spare capacity in the Netflix accounts environment. So as you can see, in this architecture, all these engines can interoperate with the same data set in the data hub, so it's very flexible. But this architecture also makes sense from the scalability perspective. So if we need to store 60 petabytes of data in D24XL, which is a very beefy storage machine already, we need around 2,500 of them. And if we want to achieve three-way replication to have resiliency in just one zone, we would need to double the cluster size, the Hadoop cluster size we have. So ultimately, this architecture also allows us to scale compute and storage independently at their own pace. So at this point, let's address the elephant in the room. So how did we handle the trade-offs of eventual consistency and the performance impact? And I'd like to share some of the thoughts that we have around the performance that we're seeing. In terms of eventual consistency, updates is one of the eventual consistent operation in S3. We work around it by completely sidestepping it. So whenever we need to update data, we create a new key, meaning a new file name, and then delete the old one. By doing that, we're only creating new puts in S3, which is a strongly consistent operation. List is another very important operation for us. It is also an eventual consistent operation. What we need to know is when we do a listing, we include all the files that we need, and also not including files that we deleted, right? Because listing could list file that has been deleted. So what we did is 2 years ago, we implemented Zamper, which is a system that we open source in Netflix OSS. What it allows us to do is to keep track of the files or a manifest of files for the prefix that are generated by upstream job, so that downstream job know exactly what to look for and expect, and we store that manifest in DynamoDB. Subsequently, Amazon EMR also implements something very similar called EMR-FS. So in case any of you are using Amazon EMR already, listing consistency should not be an issue. And then I'm going to talk about performance. Before I talk about performance, I want to mention that we're using Parquet file format. And it is, Parquet file format is a Apache open source project. It's interoperable with all the engines that we choose. We have engineers in the team to help improve Parquet efficiency and performance so that we could close the gap of S3 performance versus reading or HDFS, the performance of HDFS on local disk. And all the performance number or performance thoughts that I'm going to share is based on the fact that we are using Parquet file format. So one of the main benefits for Parquet is read performance. Both column projections and predicate pushdown means to reduce the amount of data that we need to pull over the wire when we read from S3. Parquet is a columnar file format, so it allows column projection. If you are selecting 1 out of 50 column, it only reads 1 column over the wire. Similarly, Parquet also groups columns into row groups. At the end of the row groups, it would have statistics. So in case you are selecting data based on some predicate condition, and if it cannot find these predicate values in the row group section based on the statistics, what it would do is also completely skipping the row group. So these are tactics that it would help us to actually reduce the amount of data that we read over the wire from S3. It also supports the vectorized read. What it means is when it reads a whole column, it could read it in batch instead of reading it row by row. So it reduces the number of seeks and round trips to go to S3 as well. So even given the performance, even given the fact that we are using Parquet, we are continuing improving it, we're still seeing performance impact. So I'm going to share some of our thoughts around that, as well as some of the things that we are thinking to continue to improve on to narrow that gap. In terms of read performance, of course, it comes from throughput and latency impact, right? For simple queries, let's say you're doing a count star, round trip going to S3 dominates. Latency dominates the time that you spend on the query, because in Parquet file, all you need to do is to read the footer and get the count. In those cases, query run fast. However, the performance impact in terms of percentage is high. On the other hand, if you're running an ETL job that you're selecting 40 columns out of 45 columns, you're pulling a lot of data over the wire from S3, the performance difference is huge. However, your job is also going to take a lot longer to run because you need to deserialize the data. You're likely doing a lot of complex computation. So at the end of the day, the performance impact in terms of percentage is actually lower. And one of the improvements that we can still improve read performance is to improve the IO manager in Parquet. What we want to do is to do parallel read on column chunks, as well as reading adjacent columns together to reduce the number of seeks. So these are things that we are thinking about doing to improve in Parquet file format in order to close the gap. In terms of write performance, if you could think about big data processing job, what it does is it has a lot of parallel tasks, all processing different data sets. They're writing output into local files. When the master of the client know that all the tasks are finished and done, it's going to do a commit. During the commit logic, what it does is each of the parallel tasks is going to do a rename to put the file into the final location. The output files in the final location, but S3 does not support rename. So what happened? So what happened is in these big data processing engine, they write to local disk before uploading to S3 at the very end and introducing an extra hop and latency. So one thing very obvious that we could do is to improve the commit logic for these big data engine to do direct writing onto S3. And we'll leverage the semantics of how multi-part upload works on S3, in which if the jobs actually failed at the very end, we could actually abort multi-part upload across all the parallel tasks, so no files will be written on S3 and it's still consistent. In terms of listing, the biggest penalty comes from when the job startup time in a big data processing job. If you could think about in a big data processing job, at the job startup time, what we do is do a listing to find out all the files we need to read as input, right? And the client is going to list all the files, look at the size of all the files, and do a split calculation. To do that is actually make a lot of round trip to S3 to list out all the files that it needs to read, and usually it needs to do one listing per partition. And in a big ETL job in our environment, we could be doing thousands of them. So job startup time is usually a bottleneck for us because of the listing latency. So what we could do, and this is something that we're thinking right now, is instead of tracking prefixes for these partitions in the metadata, we're tracking the actual files. If we do that, we could completely skip the necessity to do any listing. So these are some of the things that we are thinking about to continue to improve to close the gap. To summarize, for big ETL jobs in our environment is very CPU bound, and performance when you compare using S3 versus using HDFS on local disk converges as the complexity and the data volume increase. For interactive queries, by the virtue of the fact that interactive query, you are reading a lot less data. So mostly it is the latency that is dominating. So the percentage of impact is higher, but these jobs run really fast. In our environment, the median execution time for our interactive Presto query is 3 seconds. So we are not talking about a lot of wait time. So at the end of the day, all things considered, all the work we've done, we still think the benefits of using S3 outweigh the cost. And that's why we're here today to talk about our experience. So let's talk about how we manage the 4 different engines that we have. Different versions of them are running across, let's say, 10 different clusters. How do we manage that combination? And what are the most common problems or questions from our users? They want to know where they can run the job. Should they run the client on the laptop? If so, what version of the tool should they install? Which cluster should they pick to run the high priority job or the backfill job? They don't care where you run the job. They just want to see all the jobs in one place. From administrative perspective, like people in the big data team, they want to be able to know exactly what version of what tool is installed in which cluster. And they also want to have the freedom to be able to swap out cluster and do deployment and upgrade without user impact. So with that, we designed and implemented Genie, which is a job and cluster management service. It solves all of the above problem. It allows users to discover the cluster to run the job. It also acts as a gateway for them to run the job on so that they don't need to run it on their own machine. And also is a one-stop shop for them to see all the jobs that they've run. From an administrative perspective, it is obviously a configuration management tool. It manages all the different tools and versions across all the clusters. It also allows us to do very easy deployment. So at Netflix, whenever we need to upgrade a cluster, what we do is we spin up a new cluster, register it with Genie, mark it as up so that users, when they submit job, it will go to the new cluster. Then we mark the old cluster as out of service. Job will continue to run, and we'll wait for it to finish. When it's done, we'll shut down the old cluster. So everyone is going through Genie to get access to the cluster. And Genie also uses S3. We use S3 to store the archive job output files for 90 days so that people can go back and see. Also, it is a place where we put all the job executables, tools or engines, cluster configurations, so that it can be shared across all the clusters. Genie is definitely open source on Netflix OSS. It's been open source for 2-3 years now. We just released 3.0 internally at Netflix, and it's running in production for 2 months now. So if you have a similar problem like we do, have a complex system architecture, I highly encourage you to take a look at Genie. We are going to publicly announce 3.0 towards the end of this year or beginning of next year. And the only thing that's holding us up right now is our favorite part of engineering, which is documentation. Other than that, you can use it. So we've been talking a lot about the object size, how many objects we have on S3. How do we manage them? What is the brain behind it? So for all the data that we store on S3, we use Hive Metastore to store the metadata for the data on S3 Data Hub. It works well. It interoperates with all the 4 different engines that we choose. But we didn't stop there. We actually built a centralized metadata service called Metacat so that all the 4 different engines can interoperate with Metacat and proxy the request back into Hive Metastore. So what is Metacat? It is a federated metadata service. It is a proxy across all the data sources we have. And the keyword is proxy. Metacat does not actually store the metadata for the different data sources. It's just a proxy back. So Metacat obviously proxy the request to Hive Metastore. There are 3 additional data stores that we use. So it proxied the request back to Redshift, Teradata, and Amazon RDS as well. So why did we build Metacat? It allows us to provide a common set of API for all the tools and applications that we built in our platform. Kurt is going to cover more about the applications and tools that we built in the big data ecosystems that we have. It also supports Thrift API, obviously, so that all the 4 different big data processing engine can interoperate with it. It allows us to do metadata discovery across all the different data sources. The single most important reason why we do it is also because it allows us to put additional business context across all the data sources. For example, we can put lifecycle policy across all of them. We can tag the different table, put additional metadata. We can put in user-defined custom metrics across different data sources. And Metacat currently is checked into Netflix open source GitHub project. We do have planned to open source it next year, but I don't have a specific date at this point. So how do we manage the data lifecycle? We expire 400 terabytes, right? How do we do that? Unfortunately, we cannot leverage the S3 lifecycle policy because we have more complex business rules. So we end up building a set of janitor tools, much like the janitor monkey we built to clean out EC2 instances and EBS volumes. So we delete dangling data after 60 days. What is dangling data? Dangling data are data in the data hub that are not referenced by the Hive Metastore. These are dangling data. We delete it after 60 days. And there is a special case, which is when we do data updates, we create new keys and delete the old data that I mentioned earlier. In those cases, we delete it a lot sooner. We delete it after 30 days. And then, of course, the other tool basically delete the table partitions based on the table TTL policy. But our deletes patterns is pretty spiky. If you look at this chart, on one fine day, we're deleting 20 million objects. And actually, it didn't happen on that day. It happened in the span of probably 10 minutes or 5 minutes when the janitor tools is executed. When a janitor tool is executed, maybe somebody changed the TTL yesterday to reduce it, or somebody decided to drop a table. So we need to handle scaling S3 deletes. And what we did is we built a Deletion Service. It is a centralized service to handle errors coming back from S3. When we do a lot of deletes, we receive 503 from S3 asking us to back off, and so we do exponential back off in the service. It also has a very cool feature called cooldown period. So whenever users want to delete partitions, what we do is We delete the metadata first, let the data stay in the data hub for a few more days. In case they regret it, they just need to recover the metadata and don't need to recover the data. And of course, having one centralized service allows us to store history and statistics, and also allow us to have easy recovery in case we do need to recover the data back from the S3 data hub. So with that, I'm going to hand the baton over to Kurt to continue.
Thank you very much. Or the clicker in this case is the baton. So I'm going to continue our journey into our big data ecosystem through the lens of S3. I'm also going to throw in some tech philosophy to hopefully keep you guys awake during this process. But I'm going to start with a very glamorous topic of backup strategy to really keep you riveted. So for starters, like, how do you back up 60 petabytes of data? That's pretty challenging. Fortunately, core S3 provides a lot of the capabilities out of the box. So we use version buckets for just about all of our data. That will do soft deletes. So if somebody regrets later on, like, oops, I made a mistake after the few days of the cooldown period that Eva mentioned, we can go back to about 20 days for most of our data. We've created a tool that lets us easily recover the data from S3, and it's a little bit more manual to actually get the Hive metadata back and the Metacat metadata back. We have to do a restore of those databases. And it seems like, well, why don't we just build a tool for that? And we probably will at some point, but just the effort versus the value is not there. So I guess that's philosophy number one, like, don't over-engineer until you need it. As far as 60 petabytes, the beauty of S3 is it implicitly handles the scale, not only for the active data, but also for the soft deleted data. And I used to manage a lot of stuff in a data center, a lot of like MPP, huge databases, huge meaning like hundreds of terabytes. And it was just so painful, backup strategy for that. I mean, you have throughput considerations, you have pre-provisioning, you got to get that right. You have like flaky tapes, and you don't have any of this with S3. You have 11 nines of durability just waiting for you. So it takes care of, it's just simple. You don't even have to think about it. But in and of itself, we don't want to just keep data in S3. So what about our really, really important data? Well, interestingly, a sort of secondary effect of the fact that we use other data stores and other data processing engines, we also have some of our really important data in other data stores for fast analysis. So two examples are Redshift and Druid, which I'll cover later on. We also, don't tell anyone, have a heterogeneous cloud platform, despite being in an AWS conference. So we do put a little bit of data into the Google Cloud. So this is our really important customer type data. It's encrypted, but if we really had a disaster, like a huge, huge disaster, which would never happen at Amazon, then we'd have some way to get it back. And we've also been dabbling with cross-regional replication and working with the S3 team at Amazon quite a bit to try to figure out how can we really turn this into a full-scale disaster recovery solution. And we are using CRR just a little bit on my team right now, but not currently for the massive 60 petabytes. On the data accessibility front, so our general philosophy is really simple, is that we just like to keep everything open in the data warehouse, which unfortunately, probably for a lot of you, is not an option. You might have to get down to like row levels and columns, and this person in finance can see this, and this other team can't. We don't have any of that. Everybody can see everything in the data warehouse. And the reason we do that is that this data is gold that Eva talked about before. Like, we want to get that gold out in everyone's hands, not spend all this time with security policies. Well, how can we do that? Well, the way we are able to have an open window, I guess, is to have a closed door. I don't know if that's the best analogy. But what we do is we just keep personally identifiable information out of our data warehouse. There is some analytic value in terms of someone's address, but when we weigh the benefits of an open system versus this limited set of data with limited use cases, we'd rather just keep it open and keep that data out altogether. We do have some provisions, though, some automated checks and even some manual checks to make sure that nothing seeps into the data warehouse over time through that massive pipeline that Eva talked about. On the data tracking front, we have a multivariate approach to how we track our data. We have a lot of automated ways to say who is doing what in the system, but another philosophical principle is often we just count on people to tell us who they are, which sounds, again, like a little strange. Can you count on people to like properly tag their data? If someone runs a Genie-Job, like who are they? And in that Genie-Job, they can specify the right user that we can then tie into reports that have proper business context. If it's like user X, I don't know what that means. If it's the marketing data analytics team that's running this job, I know who's neck to strangle when the system is going haywire. And where do we put the data? So whenever we run these data processing jobs and we put data into S3, the user agent, we fill in all sorts of rich information so that we can track down who's actually writing this data. So we have things like the job ID and the cluster ID and the task IDs and the user ID. All of that is stored in the user agent for easy processing. And we've written some Spark jobs that go through the S3 access logs. They figure out who's using what, figure out if nobody's using it, we might have an opportunity to get rid of it. Or we've even got Amazon contacting us in some cases saying, can you please stop hammering S3? And in that case, we will go into Presto typically and query the table that has these S3 access logs, and then go to the developer and be like, I know this is infinitely scalable, but can you please ease up a little bit? We also have a metrics pipeline. So for our jobs, as they're running, they're collecting all sorts of metrics, like the job history files. So we take these history files and we put them down the same data pipeline that Eva mentioned before. So instead of like reinventing a wheel of how do we process all of our metadata within the data warehouse, we use the same infrastructure we've already built to feed the data warehouse in the first place. And one of the things that we send down this metrics pipeline is execution plans for our various jobs that are running. And the reason we do that is then Charlotte is a system that we built, and maybe we'll open source it at some point, that does dependency analysis and lineage across our data. So it'll take these execution plans and figure out what data is this job actually affecting. And then in addition to the data we put down this pipeline, we also have parsers that look at Teradata queries and Redshift queries and Hive queries right now and figure out what are they affecting. And by having that information, we can do really powerful things, and I'll talk about that later on. So are we going to get it all right? Are people going to correctly identify themselves? Are we going to have a perfect parser that's going to get every job dependency? There's no way. And we don't even try to a certain degree. Like we do the best we can and then let it run. And then, an example of something for efficiency, we might say we're going to delete a bunch of data because nobody is using this anymore. And we might be wrong. And the first thing we'll do is we'll send out a spreadsheet, typically, or a Google Sheet, and we'll say, here's all of the stuff that we're about to delete. Let us know if you want to keep it. And then people will scramble around and look at the Google Sheet, and they'll be like, ah. And then sometimes they'll be like, duh. Like, this is the most important data at Netflix. Of course, everything's the most important data at Netflix. And then we'll go through and we'll be like, why did we miss this? How did Charlotte miss this in the processing? And then we just fix the rules engine. It covers that whole class of problem in the future, and then it just gets better and better over time. As far as data cost, again, back to what Eva said about data being gold, it's not the top priority is cutting costs. You can see that big dollar sign going to like a medium dollar sign instead of a really small dollar sign. And again, you might not have that luxury at your company, and I'm sorry for you if that's the case. But for us, it's like we really want to let people make the most out of this information. And interestingly, another philosophical principle is that our first calculation that we provided to people on how expensive is this data table, it included the soft deleted data. Now, technically, that is correct. That is the better measure of what it is. The problem with it, though, is that some of our good citizens would do a bunch of cleanup, and they'd look at the report and see how much space am I using, and nothing changed because it hadn't TTL'd out of the system. So we were like, well, let's actually change it to something that's actionable and makes more sense to a user, even though it's wrong. So I guess philosophical principle, better to be comprehensible than correct in some cases. We might add back a secondary metric at some point that covers both of those things. And we did do a side analysis just to see, is this soft deleted data, is that just overwhelming? And it's a small portion of our overall data warehouse. And how do we surface the data costs? Well, we use Tableau reports, which engineers don't look at, but managers do sometimes. So that's one way. You get the occasional hey, do you really mean to spend $200,000 on this table? So a manager might talk to some people on their team, just make sure it's sane. But more realistically, what you need something more tactical for an engineer because they have their day job of developing jobs and doing great things. So you need something front and center. So we created something called the Data Doctor. And this is sort of like an inbox of things that you might and you should care about as a developer. And an example that I'm showing here is all the tables that are in the top 5% most expensive show up in their sort of inbox. And it also has suggestions on here's things you might do to reduce the size, use Parquet, remove unnecessary columns, or reduce the lifetime setting. And this is just one of many, many different rules that you can set up. Others are like highly skewed jobs, or maybe if your job is really long running compared to historical trends, like all this shows up in the developer's inbox. And another philosophical principle here is, well, that's great the first time, and it's really annoying if you keep seeing that every single day, especially if you're like, yeah, it's expensive because it's a lot of data and it's really important. So we have this snooze option in that second tab, and in that you can snooze it for a week, a month, 3 months, or you can just whitelist it all together, and you're required to give a reason if you whitelist it forever, saying, it's expensive because I need it, and I've compressed it, and I've reduced columns, and I've set the TTLs, and just leave me alone, and you won't see it again. TTLs that Eva had mentioned are another way that we get rid of cost over time. So some data is 90 days TTLs, some is 7. It really depends on, do you need that atomic data for a long period of time? And then some things that we're considering doing to reduce costs. One is we have a lot of rich job cost information, and we have a lot of data cost information, but we haven't really tied it together very well, and it really is a holistic picture. It's not just what is the data cost, it's also what is the processing cost of that data. And then also, we're not heavily leveraging SIA or Glacier right now. It's being used in spotty ways throughout Netflix. There's increasing appetite to use it, but it takes a lot of analysis, and for the most part, we want people to run quickly, but it's an opportunity for us. Since this is big data through the S3 lens, I want to talk about some other technologies we have, and then ways that S3 is playing this best supporting actor role for us. So for Redshift, like how does Redshift really benefit for us from S3? So for starters, like why do we use Redshift if we have Presto and we have Hive? It's really good for fast interaction on subsets of data. So we let a user push a subset of information into Redshift, and if they want to do fast interactive analysis, they could do it, or connect reporting tools on top of it. Some of our engineers use it, some don't. Some just want to use Presto, they want to use Hive, they want to use Spark SQL, and they don't have to like bother with a secondary copy of the data. Other people, if they do want to use it, we set up a process where you can just put a tag in Metacat that we said before, and every time new data comes into our S3 data hub, it automatically gets replicated into Redshift. And the beauty of Redshift within the Amazon ecosystem is it's really fast to load. I mean, it's surprisingly so. So the throughput's really good, and you can also send in compressed data directly into Redshift. And we're just doing append only anyway. So getting data in there, it's a no-brainer. And other cool ways that Redshift, this is like a godsend compared to like a data center MPP database for backups, restores, and expansion. So backups, it's continually doing snapshots to S3. So if you lose your Redshift cluster, you can regenerate it. The restore process is another, it's pretty amazing how it works. You just spin up a new cluster, and then you can start using it right away. And it will fill in the data that it needs, and if you actually do a query and the data's not there, it pages the data in from S3. And then expansion, there's a couple different ways. You can expand your system without using S3, but you have to put it into a read-only mode, and you add new nodes, and you can still query it. We've tried some other novel ways of using S3. One way we've done it is that we have our main cluster here. We start up another Redshift cluster. We put the main cluster in read-only mode except for ETL. So we can keep the most of the data up to date in this core Redshift cluster. That's where people go. In the meantime, we spin up another cluster, we let it hydrate, we resize it, we play all the ETL on top of it, and then at a certain point, we just flip the people over there. So they've gotten a relatively current system throughout this whole expansion process. Druid, I don't know if many people are using the system. Actually, out of curiosity, how many people in the room are using Druid in your companies? It's a very small set. So we didn't have it in our ecosystem for quite some time, but we started finding that some cases the out-of-the-box visualization tools weren't cutting it. They couldn't handle like billions of rows that you want to slice and dice on the fly. So Druid is really good for interactive response time at scale. So some teams started creating custom visualization type apps, like really rich business applications on lots of data, and they were using Druid as a backend. And the way it uses S3, Druid uses S3 is it's a source of truth, like everything else. The data lands in S3. You might do some ETL processing. But then it uses it as like a secondary source of truth. So our indexing jobs that get data into Druid, the deep storage that underlines Druid is also in S3. So the sort of post-processed Druid-ready files that get loaded into historical nodes in Druid. So again, it's a pretty good story for having S3. Tableau. Yet again, S3 is the source of truth, like just about everything at Netflix in the big data space. However, it's mostly extracts that we're using for Tableau. So we're not directly connecting to S3, and we're definitely not using the ODBC driver for most things. That's a total disaster. If you have any questions on that, you can talk to me later. But we've worked out a programmatic way instead of filling in the extracts for Tableau. And the one way that we are using S3, interestingly, this is the one cross-regional replication case that we're using on my team, which is that when we back up Tableau itself, we also cross-regionally replicate Tableau, at least our setup of it. Now, another philosophical principle that has been hugely beneficial to us is that we've created this thing called the Big Data Portal. Like, this is almost like an alphabet soup of so many technologies that have been thrown at you. Imagine you work at Netflix and you got to use these every single day. So we honed in on a strategy of saying, well, let's just have a one-stop shop where you can go to do big data stuff. And the sort of initial carrot was really simple. It was a query pane where you could enter the query. And some of our most technical power developers are like, this is a total waste of time, this portal. Like, I know how to use all my special fancy tools, and I don't, let me keep my Unix editors whenever I want them. But over time, like, everybody uses this now, because what has happened is it's a place where people go, so we can invest in it. And because we're investing in it, it's a better place to go, so we invest in it more, and it's just gotten better and better over time. So you can see in a drop-down, if your eyesight's good, Presto is the current engine that you can running. You can change that to Spark SQL or Pig or Hive or Redshift or Teradata, whatever you want in one little pane, and you can query any of these data sources. You can switch to a test database. You can save your queries. It has auto-completion. And then on the left, you see things like the data doctor alerts. So that's the inbox that I was showing before. There's also a whole bunch of other options, but two specific ones I'll call out that interact with S3 are the schema search and the S3 browser. So if I search for a particular table, in this case, geo country D, because it's something I can actually share. There's no business special value to our country table at Netflix. And this is it just sort of shows like a lot of things we've been talking about in a really simple way. So one is it's recommending for you that maybe you want to put this in Parquet format for efficiency. It also has things that we've layered on top of our ecosystem that are not even supported in Hive. Things like default values, that when Pig is writing data, it can use these default values, or foreign keys and primary keys that you can do audit checks on. In this details tab that I'm not showing right now, it has the TTLs that you could set. I want 90 days or 7 days. It's just one place that's really obvious where to go. The Charlotte data that I'd mentioned before, you can see this is another tab. This is the data dependencies. So you can see this particular table was loaded by this pig job, geo country D pig. And then here's all the uses of that data. So if we're trying to figure out like, hey, I need to change this table and I want to notify all the users, you could see everyone who's using it. Or if you're like, I want to retire this because I don't think anyone's using it, you could see if anyone's actually using it. Or probably the other way around, it could be that you are using it in a lot of places, but nobody's loading the table, and that's a pretty scary state, which happens occasionally. And then another really powerful concept that has worked well for us is that underlying the portal and our whole data platform, we've created a lot of Python libraries that do anything you want to do on the data platform. So if you want to move data, for example, between Hive and Redshift, it's just these two Python statements. You import the module and then go. And then underneath the scenes, this creates a load-ready file on S3, of course, because this is an S3 presentation. It deals with like date type conversions between the different systems. It does gzip compress. Like everything just sort of happens for you underneath the hood. And then taking it up a level, as they're sort of coming to the final stretch here, is that here's another sort of picture that re-summarizes what Eva and I have talked about from a different perspective. You can sort of see S3 is just in the middle of everything we do. The pipelines coming in, the processing engines, the additional data stores, and the reporting tools. Like S3 is just front and center. So what are some things that are on the horizon for us on the S3 front? One is we've toyed with the idea of adding caching for a long time. We may not ever do it. Back to the performance implications that Eva talked about. Really right now, like Redshift, would probably be our caching layer, or Druid would be it. And then most jobs don't really need it. But if we really wanted like Presto to be that much faster, we might consider adding a caching layer in the mix. Storage efficiency is something we definitely are looking at pretty heavily. So this is things like, should we use SIA or Glacier? Should we use Charlotte and the S3 access logs to figure out who's actually using the data? We recently added Brotli compression to Parquet, so that's like 20% more efficient for that. And then something that we might do next year, this is a little more grandiose with 60 petabytes of data, is create a data analyzer that goes and looks for lots of small files in S3 and combines them into larger files, which is the much more efficient way of going for big data processing. And then we're continuing to partner with the S3 team and Amazon for our sake and hopefully for the community's sake. For example, the cross-regional replication for disaster recovery. And then I'll leave you with super short, sweet, simple takeaways. Amazon as an S3 data hub leads to happiness, so do that. Don't try to do it all at once though, or you'll lose your mind. So everything we started in around 2010 with Java MapReduce and Hive on S3. So that was basically our world, and then all this stuff over the years has sort of layered on top of it based on business needs. And those business needs really do take an ecosystem. Like we could not pick one tool. If you have small data and you can fit it in Redshift and write some Python scripts, that might be fine. But as it starts growing and growing and growing, you can just make that trade-off is what is the effort versus what is the value. So with that, I want to thank you and say we have office hours tomorrow at 2 o'clock. We have a Netflix booth in the Expo Center. So if you want to dive deeper into it, like how to get data into Tableau, without using the ODBC driver, or if this sounds so awesome that you really want to work at Netflix, then happy to talk about that. And please complete your evaluations so that you can say, hopefully, that this was great. And if not, you can tell us that as well. And if you have any questions, then fire away.